So I want to talk today about about what can make your Play application slow and some things that you can focus on, to address them. The title is a bit clickbaity. Should note that most of the things I'm going to be talking about will also apply to JVM apps as well, other JVM apps. Before I begin, just some background. Yesterday, Luke mentioned that Hootsuite has been moving towards microservices for over the past few years. And over that time, we've built services on Akka HTTP, Go, but a lot of our services are built on Play framework. Play is awesome. It's fast out of the box, it has great documentation. So I want to talk a little bit about monitoring, just a brief overview, the types of things you want to monitor, some tools that are out there, and I'll cap that off with a quick demo of a tool that I think is pretty cool. Thread pools, I want to talk a little bit about what they are, why they're used, the ones you'll see in Play, some potential gotchas with their config, and we'll end by showing a quick demo of why you may want to use a separate thread pool. And garbage collection is probably one of the biggest causes of slowness in an app. We'll talk about just what it is in a nutshell and some ways to give you insight on what your garbage collector is doing so that you can tune it. And I'll do a quick demo there as well. And finally, I want to finish off with a story about Owly and what has gone wrong with it there. So monitoring, it's kind of self-evident. We all kind of do some monitoring within an app, even if it's just application logs. It's important from an operational standpoint. Things like health checks. Slowest kind of app is the one that isn't running. And you want alerts if the disk on, say, one of your backends is getting full. So there are operational concerns. But you also want data about your app while it's running. Not just a record of your system over time, but you want a baseline for your system. So things like metrics. How long do some requests to an API take? Or how many times was it called? You may also want host metrics, CPU usage, load, and so forth. An example of something that provides these is stats-t. And then there's logs, error logs, GC logs, because obviously you want to be able to do some forensics and ideally get alerts, for example, if error rates skyrocket. There's also application management platforms like New Relic. Does anyone here use an APM at their work? What do you guys use?
Scala.
Ah. Oh, cool. Yeah, New Relic, Dynatrace, and Astana. So they do metrics as well, but they're kind of cool in that they can give you transactional views into your system. And so say from a request through the front end all the way to the back end into the database, you can get data about each of those segments along one round trip. And there's one particular tool that's kind of neat, Come On. Kind of does metrics and can also have some instrumentation as well. I just want to show you that really quickly. So let's see. First, I'm going to start a Docker container that has Grafana Graphite. KO. just going to start this app here. This app is This app doesn't do much. It's basically just configured to that works better. So this is the application.conf, and it's just we're configuring, what kind of metrics we want to see for ACA actors, dispatchers. So come on, it has a core that can give you metrics, and there's plugins for ACA, Play Framework, and others, and you can get metrics and traces even for your application. Turn that off. So, just going to run this app. All right, it's up. I'm just going to hit endpoint. Sorry, you guys can't see that. Go and just hit that a couple more times. So inside my just going to add a data source. So I'm just starting and bring up a new dashboard here, and my browser would cooperate with me. Add a graph, and I just want to show you, instead of me poking around in there, show you this. Okay, I'm not sure why it's not showing up, but you should be seeing metrics on this dashboard. Anyways, the tool is pretty cool. You can get all kinds of stuff, and it's pretty quick to get started. You don't need to write your own, you don't need to include your own StatsD reporter. It's kind of just comes out of the box. The only complaint I have about Come On is that the documentation is kind of in flux all the time, and they even give you that warning on their website. Okay. Back to the slides. There we go. Okay, so thread pools, they're just a managed group of threads, so you can avoid creating a new thread with each task that you want to run. And so tasks get submitted to the pool, and the pool runs those tasks on free threads. It's basically an execution context in Scala land. You already know this if you've used futures. It's that parameter that you pass in. Something needs to complete that future, and that thing is an execution context. In Play, you'll probably use two different kinds of thread pools, fork join and thread pool executor. Fork join is the type used by Play's default execution context. It's backed by a fork join pool from Javaland. In previous versions of Scala, it's using a forked version, a fork join pool. Underlying the pool is a work stealing algorithm. And as you can see here, there's a main queue where work gets submitted, and workers take tasks off of that queue and do the work. And if when the worker is finished with all of its work, if there's tasks on other worker queues that it can take, then it takes that and pulls that work, hence the work stealing algorithm. Here's an example config for an execution context backed by fork join pool. Here we're saying that we want a parallelism of 100. In other words, 100 threads. Of course, you may have this, one gotcha with this is that it's not necessarily the number of total threads that you may have. It's the number of running threads that this controls. This may be important if you're running this, if you're running on a machine that has resource limitations. Thread pool executor is a simpler kind of thread pool. You've just got one task queue, somewhat dynamic pool size. Task comes in, and if there's no free threads, and if the number of threads in the pool aren't at the max size, then a new thread gets created. Potential gotcha here is that the task queue defaults to unbounded, so just need to keep that in mind. So what are they good for? It's good for when you have blocking I/O or in CPU-intensive operations, and you'll want to run those in a separate thread pool to avoid blocking tasks or execution on the main thread pool. Just go through this dance again to try and get out of full screen here so I can show you a quick demo of what I mean. Close that. So really simple code here, right? So if we, in this example, we have blocking endpoint is just sleeping in a future. And I just want to show what this looks like. Wow. So I'm just running a bunch of requests against. Try this again. So I'm making a bunch of requests against this blocking endpoint, and I'm just going to hit this regular endpoint, and you can see that this hey endpoint is taking a very long time to run because all of the threads are being taken by that blocking execution. And of course, if I can fix this by just declaring an execution context, and then using that for my blocking operation instead of the default one. Great, it's back up, and if I run the same thing, with that blocking operation, you can see that my previous really slow hey endpoint is now running just fine. Okay, so garbage collection. In the worst cases, they can introduce latency spikes of several seconds into your application. So I'm going to try to give a quick overview of Jvn Memory and Gc. The idea behind Jvn memory layout and Gc algorithms is so-called weak generational hypothesis. It's the idea that most objects don't stick around for very long. So here we have a simplified diagram. There's roughly three different areas of Jvn memory. You have the young generation, old generation, and metaspace. Young gen, as the name suggests, is for newer objects. Old gen, objects that have been around for a while. And metaspace is the area where your classes, class metadata, and other stuff are, and we won't talk about that. Young gen is separated into three more areas. You have Eden and the two survivor spaces. So the general flow from allocation to GC is you have new objects that go into Eden, and at some point there's a threshold for Eden fullness is reached. You're starting to run a space in Eden, and that causes a minor GC event. What happens then is the object hierarchy in your app gets traversed, live objects in your young gen are marked, and surviving objects in Eden and the current survivor space are copied to the other survivor space. So at any given time, there's always one empty survivor space. Major GC happens when your old gen, the tenured space there, is getting full. And kind of happens the same way. There's a traversal of objects, and dead objects are swept away, and sometimes a compaction phase occurs. Full GC happens when the heap is full or when the collector thinks it's going to be full, and this is a minor and major GC event, and it'll be the slowest kind of event, obviously, because it's got to clean up everything. And the key thing about all this is that these pauses, these events are all stop the world events, which means that all of your Java threads in your application are stopped. So you'll want to minimize the time taken for these GC events in your application. How long is too long for a GC pause? That depends on your application and its users. If you're working on a trading platform where you're doing microsecond optimizations, then that's going to be quite different from a CRUD web app. There's a lot of GC options to go over. For each collector option, you're choosing an algorithm for the young generation and for the old generation. You'll almost certainly be using a parallel young generation collector. There's a handy cheat sheet by Alexei Rogozin, which I won't click because having troubles coordinating with my machine here. But all of this so far is very hotspot specific. Other JVM implementations may have different GC collectors. Does anyone use any other JVMs aside from Hotspot or OpenJDK? What do you use? Sorry, IBM?
Yeah, I use the IBM one. Just
Cool.
because I work there. Although to current employer.
Ah, nice. Yeah, there's a couple of other ones up there. C4 from Azure, they claim to have a pauseless GC, and there's also Shenandoah from Red Hat, which is supposed to be kind of like G1 GC, but better for massive heaps. So now that we know that there's these pauses, we want to be able to see what's going on in our application. So there are some useful flags that you can provide to your app to get more information. First three here are just giving more details about which events are happening in your application. Next set are for logs, because the first set just print everything up to standard out. So we want to have some log rotation and maybe specify where the logs are. And the last one's kind of maybe useful for debugging. You just kind of get a listing of what's in each region of memory with every GC event. You should also know about save points. Save points are when all of the Java threads in your application are stopped. And this happens all the time. There's this regular kind of where the JVM runtime regularly basically commands all of the threads in all of the Java threads in your application to come to a stop, so that the state of the application is known. And when everything's stopped, the JVM runtime can do certain operations that require some stable state of all of the object references. For example, garbage collection, that requires a save point. Same with dumping the heap or doing a thread dump with JStack. Certain profilers also require a save point in your application for them to run. And so it's important to kind of just keep this in mind. Basically what happens is one thread will basically if you have a lot of threads and some threads are taking a while to get to a save point poll, then your TTSP, your time to save point, can be very large, and there's cases of some applications never even stopping. And Nitsan Wakart, who's a JVM engineer, he has a really interesting example where you can have an application that will never stop because a thread never reaches a save point. So there's a couple of JVM options to kind of give you statistics, give you insight into the times when an application stops, other than GCs. And these flags are not named very well, but you have this one that's kind of telling you how long an app was stopped for a save point. You can also find out how long an app ran between save points, and you can also get the cause of a save point. Okay, another demo. So I just want to show you. Let's see here. So I don't know why my pinch to zoom is not working. So using accessibility feature here to zoom in. So I've got another contrived app that is just creating a lot of garbage. It's got a slow actor, and and it's just sending really heavy messages to that actor, large arrays. Okay. Why is it complaining about that? That looks okay to me. See, so sorry, in this, I should explain this command line. So I've got all of those Gc information flags, logging to a log. I'm printing save point statistics. Maybe I need that. Okay, that's better. And that's not what I want. So let's have 2 threads, 1 connection. Let's run this for 100 seconds. And what I'll do here is I'm just going to run this with Java Mission Control. Actually, maybe I should start this app first. All right, it's running. Does everyone here have a favorite profiler? Does anyone use Java Mission Control? Oh, nice. I don't know why it's not moving. Come on. Oh, okay, there we go. So it comes with the JDK. It's free for development use. You got to pay to use it in production, though. So I'm just trying to start a recording here. Okay. What is it not like here? Iterations right.
Connections must be greater or equal to threads.
I'm sorry?
Connections must be greater or equal to threads.
Oh, thank you. So there's the GC log that I'm tailing. I don't know why it's not. Would help. There we go. So you can see there's a bunch of GC allocation failures, and that's a minor GC event. And here we've got the seconds since the VM runtime started. Got the Jvn collector there is saying, can't see it there, but saying what it started, what the Jvn space started with and what it ended up with, and so forth. Most important bit is the real time. You can see it's taking quite a bit of time to do the full GC. It's taking up to a second by this point, and I should have, surprised it's not, hasn't crashed yet. So pretty cool because you can sort of see what's going on. Kind of combines a lot of the information that you can get from other tools. You can see here, it's kind of hard to tell. I don't know what's going on with my screen here, but you can see the size of the heap increasing over time. And if I can slow it down, scroll down here. You can see the pauses as well. And you can also see Gc times, and you can see how they're going up over time. All right, let's turn this off. Please bear with me. I'm having technical difficulties here. I'm not sure why. Just close IntelliJ here. There we go. Don't need that anymore. Not sure where my Chrome went, though. Okay, I'm not sure where my slides went, but let's see here. I'm sorry? Control left? No, it's not working. So I do see, oh, there we go. Thank you. Thanks. So I want to conclude with the story about Aule, like an outage story. Does everyone know what outle is? It's our URL shortener at Hootsuite. No? Oh, it's our URL shortener at Hootsuite. It's used, we have a UI for it as well, for anyone who wants to shorten URL. But we also have public APIs as well as private APIs. So it services the Hootsuite dashboard for users who want to schedule messages and have URL shortened in their message as it goes out. So the reason why I want to talk about this is because it kind of ties into some of the things we've seen. This was in May of last year, 2016, and ops engineers were getting alerts. Aule front-end nodes were going down, and wasn't too many of them, so there wasn't a lot of customer impact. This is roughly what Aule looks like from an architecture standpoint. You've got the load balancers. The web nodes is what the story is about. There's talks to S3 and has a cache layer. And then behind that, there's the data nodes and database. There's actually two of them, but that's besides the point. So the web nodes do quite a few things. They handle redirects of shortened URLs and image URLs. They also handle image uploads. We have an image upload API that's used by our Hootsuite dashboard. So in May, when these nodes were going down, you can see the execution time on UI and other places went up. This is kind of cumulative time across nodes. And it was also affecting clicks. You can see that the time for a click was going through the roof. And these nodes were going down due to out-of-memory errors. And you can see the Gc time go way high. and the reason why this was happening was because when image uploads were happening, the entire image was being put into memory, and image was being scaled, converted to a image format like JPEG, and all of this was being kept in memory as it was completing this upload to S3, the image upload. And so this was kind of happening when S3, when it was taking a long time to upload images. So if S3 was taking a long time, if there was a slowdown, more and more of these images, these byte arrays would stay in memory, and the app would eventually not be able to keep up with garbage collection and go down. So the solution to this was to throttle the uploads. So we added an ACA component, ACA actor component, to basically receive these requests and throttle them to the S3 image uploader. This worked fine. This worked fine, except the throttling was being done at the component layer, and so you would still get a bunch of requests coming in and hitting this ACA actor, and unfortunately the mailbox was not bounded, so the mailbox would fill up and you'd also run out of memory, and so sometime later we came across the same issue, and nodes would start dying because they're running out of memory in that case. So the solution to that was to move the throttling up to the action itself in play, and not submit the request to the component. And so we've talked a bit about monitoring, garbage collection, threads, and shared a story with you guys. Thank you. Does anyone have any questions? Yes.
So I have two questions. The first is, you spent a fair bit of time talking about or monitoring Gce pauses.
Right.
What information do those actually give you? The second question goes back to something you mentioned earlier in the talk about thread pool management. You showed this pattern where you keep a separate thread pool for I/O operations, for I/O bound operations, than you do for in-memory bound operations or CPU bound operations, which is a pattern that we've been following. But while there's a fair bit of information out there about best practices for the CPU bound thread pool, basically you look at the number of available processors you have. Number of threads in the CPU thread pool is somewhere between 1 and 2 times that. I don't have any sense of what good sizing for the I/O bound thread pool is. Do you have any experience you want to relay on that?
Thanks. For the first bit about Gce pause times, I guess it's just something to be aware of. I mean, I've seen applications where Gce pauses were taking up to 5 seconds, for example, and that's a long time. If your app can tolerate that, if it's something, for example, that's happening asynchronously, work is, this app, this JVM is doing work asynchronously, and there's no user kind of waiting for those occasional requests that can take that long, then that's okay. I don't know if that answers your question for that first one.
So Gce pause means the main thread is paused.
Yeah, so with Gce pauses, it means that all of the Java threads in your application are stopped, yeah. As far as I/O bound, I don't really know. A common pattern is just to have a bunch of, declare a lot of running threads available. So parallelisms of 200-300. I don't actually know what the answer is for, as far as what the best practice is. That's what I've seen used. I'd love to hear more about that, because that's something I'd like to know as well, like what other people would do. I've tried 300, 400, 200. Anyone else? Yes.
I know this was your first public presentation. It was awesome. Thank you.
Thank you.
I want to ask you what developers should do to check the performance of their application before going to production. Sorry, I'm going to repeat the question.
Yeah.
What do you think, because you show up some tools to check performance after maybe the code is on production or maybe in the developer machine, but what do you think developers should do to check the performance of their application before going to production?
Yeah, that's a good question. I mean, I guess you got to have, the test for that, some kind of, a performance regression harness. For example, Play Framework, they have their own test, what's called Prune or something, where they're constantly monitoring the performance of, their framework, over time to make sure they don't have like serious performance regressions. I don't have an answer for that, but I kind of agree that that's something you'll want if performance is a big thing. I think for the most part, if performance is not a huge issue, if you're not a web framework, if you're not a trading platform, then probably if you have issues, you'll see them, pretty soon after in staging or early on during a production deployment. So, yes.
Can you recommend anything similar to New Relic for those of us that are running applications that can't go and use cloud services?
Yeah, that's a good question. I don't have a recommendation per se. I mean, I know that I don't have one. I'm sorry.
Okay.
But maybe that gentleman over there who was using Istana, maybe he might have some information.
Okay.
On that, yeah. I've only ever used New Relic myself. Yeah. Great. Thank you, guys.